Namaste students. I am Professor Nikhil Singh. Being a mechanical engineer, I am a teacher as well. So today's topic is total internal reflection. Stay tuned with the entire complete video, and if you like the video, check all the other videos that I have uploaded on my channel. If you like them, do subscribe to my channel and press the bell icon so that anytime I upload something, you will be notified. Do share the video with all your friends so that they can also understand this concept very well. To start with, let me start with a brief introduction of refraction and then we'll move on. So, pay attention. Now let's say if you have an interface over here, I'm not going in depth right now what is refraction and all because that is already there in my playlist of refraction. So when a light travels from a rarer medium to a denser medium, it has a property that it will always bend towards the normal. Now this is the normal. This one is the normal. So the light would have went like this if the medium would not have changed, but the light will go like this. Okay? The velocity in the rarer medium is more and the velocity of the ray of light in the denser medium is less. Similarly, if the light travels from a denser medium to a rarer medium, then the ray would have went like this if the medium would have not changed, but because the medium is changing, the beam will bend away from the normal and it will go like this. Similarly, the velocity of light in the denser medium is lower and the velocity of light in the rarer medium is higher. Now, understand this concept. I'll take this thing from denser to rarer ka condition I'll take and I have drawn a diagram over here. Now, imagine a bulb. When you on a bulb, it will glow. So it will have a tendency to give the ray of light in the outward direction in all the directions like this. So ray will go everywhere. Okay. Now imagine this bulb is over here. So this spot what I am drawing right now on your screen, this is the chota sa bulb. Now when the bulb is glowing, I am assuming that the bulb is kept in one medium and that medium is a denser medium. Let's say it's water. Let us say, because you know that if you have seen a swimming pool, so inside the swimming pool, instead of having water fill inside the swimming pool, you can have lighting system inside the pool. So just imagine that this is the swimming pool. So when the bulb will glow, one ray will go here, another will go here, third, fourth, fifth. Like this I have taken 5 rays. All are going up. So the ray which is coming over here is got angle of incidence as 0 degree. It will go straight. It will not deviate. But when you are going from a denser to rarer medium, and if you are going inclined, you should have went like this, but the beam bends and goes here. So this is the second beam. Let's take the third beam. It would have went like this, but it is bending and it is going here. Let's take the fourth beam. Meanwhile, if you move on like this beam should have went like this, but it will bend and it will go along the interface. Now, if you increase this angle, see this angle of incidence. So the beam will bend and it will come back inside the same medium. Now let's see. Here you have angle of incidence as 0 degree. Here you have angle of incidence as I1. Here you have I2. And similarly, you have here I3, I4. Now, if you watch it carefully, I1 is 0. This I here is 0. I1 is chota angle, but it is more than 0. It is more than 0. Here I2 is even more than I1. Dhire dhire, the angle is getting increased. Now, at the angle at which if you put a light traveling from a denser medium to a rarer medium, and if the light goes like this, at that time this angle is known as critical angle. So when you travel from a denser medium to a rarer medium, and if your ray of light do not go into the rarer medium, nor do it comes back in the denser medium, it goes along the interface, at that point this angle is known as critical angle. Okay, and if the angle is greater than the critical angle, the beam will bounce back to its original denser medium. This phenomena is known as total internal reflection. So what is total internal reflection? When the ray of light travels from a denser medium to a rarer medium, if the angle of incidence is greater than the critical angle, then the ray will bounce back inside the same medium. Okay, now let's see in real life how does total internal reflection actually look. So this is the main diagram, and looking at this diagram I'll tell you how does that actually look. Okay, so we'll start with the setup. I've taken three things: one, a plain paper on which the angles on both the sides are marked; second, a semicircular glass lamp; and the third, a source of light. When the source of light is incident, it is going straight up, 0 degree angle of incidence, 0 degree angle of refraction. Now if you see, I am slowly and slowly increasing the angle of incidence. So the angle of refraction, see, the refracted ray is looking more bent. You're going from denser to rarer. But see, angle of incidence पे, when you have incident ray, छोटा थोड़ा थोड़ा you can see reflected ray as well. So there is a bit amount of reflected ray and refracted ray. The ray is getting bent, and suddenly approximately at 42 degree. See, total internal reflection occurs. Now, if you increase the angle a bit more, the reflected ray will move like this. So it will open up like this because angle of incidence is equal to the angle of reflection. And here you can see actually how does t.i.r occur, because it is occurring at 42 degree because it is glass slab and critical angle for glass is approximately 42 degree. So this is how total internal reflection actually looks in the real life scenario. Stay tuned for more upcoming videos on optical fiber. If you like the video, do give it a thumbs up and share it with all your friends. Subscribe to my channel and press the bell icon. तब तक के लिए पढ़ते रहें और खूब आगे बढ़ते रहें. नमस्ते.